given this knowledge of brute force being used to solve the peg solitaire game, let's show you how straightforward it can be to apply it to another solitaire variation. And again, in doing so, I'm going to demonstrate the steps that you would do to solve this problem. I'm not going to create this from scratch as I just did with the peg solitaire. Rather, I'm going to show you the implementation, and then we'll discuss some of the weaknesses of the overall approach and ways that you can even optimize further to take advantage of the power of brute force. You may be familiar with magic squares, those mathematical oddities where you arrange n squared numbers into a arrangement where the sum of all the numbers in any row, column, or diagonal is the same. This 3x3 square was known in antiquity, and each row, column, or diagonal adds up to 15. And most people can arrive at the solution after a few minutes of work. But what about a 4x4 or 5x5 or worse? It turns out that trying to arrange the numbers from 1 to n squared in f square is not easy. The main challenge is the sheer size of the search space. This is what is known in mathematics as a combinatoric problem. If you imagine how many possible ways can you arrange the numbers from 1 through 9 in a 3x3 square, start with a basic idea. In the upper left-hand corner, you can put any of the 9 digits. Well, what about the next one next to it? You've already used 1, so now there are 8 remaining. What about the next to that? Well, you've used 2, so now there are 7 remaining. And you quickly realize that the total number of solutions is actually equal to n factorial, which is n times n minus 1 times n minus 2, and so on. For a small board like this, n factorial, where n is 9, is only about 500,000. When you go to a 4x4, which is 16 total, 16 factorial is already some number in the order of 10 to the 30. So it's clearly not something you can just try every possibility. But I want to try to find some way to do a brute force approach. And so in this case, while it doesn't look the same as peg solitaire, it has a lot of things in common. I start with a board, and I add digits to the board, and each time I do so, I reduce the problem of size 1. I first start with a board with 9 empty spaces, and I add a digit. Now I've got 8 empty spaces. And I can continue. At any moment in time, there's a certain set of moves that I can make. How many digits are remaining for me to put into the neighboring square? And after I've done that, I try to solve the next recursive subproblem. And if it turns out that I put 9, 8, and 7 in the top row, and it doesn't work, well, I've got to work my way back and undo and try to find another sequence of numbers that will produce an answer. So it has the basic feel of a brute force algorithm. And what I'm going to show you is the final code, which demonstrates how to take that same approach, which we used in peg solitaire, and I'll show you the solution with a magic square problem. In doing so, we'll solve for the 3x3, and then when we solve the 4x4, you'll see that it's not going to work because it's too large of a search space. But with a small optimization, we can make it even work there. Now let's see a Python implementation that will show how to construct magic squares. Admittedly, it only works for small ones, but the proof of concept is still valid. Now to do this, I need to come up with a strategy that represents the board, as well as identifies the moves that are available at any one time. The way that I'm going to do this is by structuring the board as a two-dimensional array, and then operating under that principle all the possible moves that you would have. Here in Python, I start with a function called initialize, which will create a board that's a two-dimensional array. And I do this first to set things up, so I know what my board looks like. In this case, it's a 3x3 board, initially no values. And I need to keep track of, well, what digits am I using? I'm going to be inserting the digits from 1 to 9. And for this purpose, I'm going to have an array used, which will keep track of all the possible digits. And then the way the brute force algorithm works is you pick a certain location, and you put a digit there, as long as it's not yet been used, and then you move on to the next one. Each recursive call will therefore solve a smaller problem than the one before. And when you get to the final step, which is I have 9 digits, all one apiece in each of the 3x3 cells, only at that point can I check to see if I have a solution. So this falls into the exact same category that we had for the peg solitaire. I need to be able to represent the board. I need to have a way of representing the different moves that I have. And I need a relatively efficient way to determine when I have a solution. Let's look at the overall structure first and try to use that to understand whether we have this working. As you recall, what the solve method did is it made a recursive invocation on itself with a problem of one size smaller. The way that I'm going to set this up is as follows. I'm going to keep track of a separate variable called step. Starts off at 0. And when I started with a step of 0, that means we'll put a digit, the first digit, in the magic square cell. And do it at the upper left-hand corner. And then after that, the next step will be the one in the middle. And then so on until all 9 are filled. This recursive invocation is this key step here, which says solve the problem that's one smaller than the one before it. And when I eventually get to the end, in fact, when the number of steps that I've recursed is exactly n squared, that means I've placed all of my n squared numbers. And at that point, I check, do I have a valid solution? If it turns out that I do have a valid solution, it will return true, and the solve recursive call will return true, and then I'm done, just like you saw with the peg solitaire. Of course, it may be the case that I'm not done, in which case I have to undo that move and then retry again. So this one doesn't create a new structure for what moves are available. It takes a slightly different tactic. It says, fine, I'm going to check each of the n squared numbers from 1 to 9. And if that number has not yet been used, I'm going to claim that it's used with this array that keeps track of which digits have been used. And then I'm going to modify the particular location in the board to put this digit in its proper place. And this is a very simple computation. When step is 0, then 0 divided by n is 0, and 0 here is 0 again. So I'm going to put it into my first entry, 0, 0. As I go through, step increases to 1, to 2, to 3, and so on. And what this operation does is it places the digit in the right square in the two-dimensional array based upon the step number. When I'm finally done, I will have completed 9 steps. And that's where my termination logic holds. If I ever get to step exactly equal to n squared, then I know that I'm done. And then I move on to the isValid function. So this one actually has no moves specifically, but it has the ability to insert a digit at a certain location in the cell. If it turns out that the solve recursive call is false, then it undoes that step and claims that digit is once again available for use. So it's the same basic structure. The only thing that's changed is the representation of the board and the representation of the moves. It doesn't matter which way you go. How you choose to represent the board is fundamental to the success of this algorithm. You want an approach that's compact, efficient, and easy to determine success and the available moves. So we have that here. All the real logic happens in the isValid function, which we'll describe now. IsValid is trying to look at the sums of all the rows, all the columns, and in fact the two diagonals to make sure they all equal to the exact same magic sum. The way I have this set up is when I initialize the board, I keep track of my magic sum. In this case, it's the value 15. So to determine if a solution is valid, I have nothing more to do but to check, is the sum of all the rows and all the columns equal to that magic number? And this logic here will do it. And again, this is the result of several minutes, maybe to an hour or so of work, so you may not come up with the exact representation the first time, but after you work with the representation and the available moves, you quickly negotiate a good compromise for efficiency, compactness, and the ability to determine when a move is valid. So if I start with this basic premise, then I have everything in place. Let's run it and see what we get. So I'll initialize the board of size 3 by 3. This is what the board looks like right now. There's nothing there. I'm going to request to solve this board. After about a second or two, it comes back with an answer. And this is what it came up with. You can see that it started in the upper left-hand corner, and it started from 1, tried to put a 1 there, that didn't work. Then it put a 2 there, that one worked, after a while of computations. If I look at this arrangement, 2 plus 7 is 9, added 6 is 15, 7 and 5 is 12, add 3 is 15. So this is a valid magic square. So you might say, great, everything looks good. Well, the trouble is, what have you actually computed? Now in Python, there's a factorial function. I think it's a factorial function that would tell you, well, how many possible arrangements there are. If I know that it's n factorial, where I've got 9, I've got about 360,000. But what if I wanted to change this now to work for a 4x4 arrangement? I got 16 now to place. It's a lot more. It's about 10 million times more. So if this particular problem on a 3x3 took about a second or a second and a half, it's going to take 10 million seconds, which is far too long to run. And the real challenge then is to try to find ways to improve the performance of the algorithm. The way that this is stated very quickly, as you see here, is nothing more than a brute force approach to try every possible digit in its place, regardless of how successful it might be. So I can actually start to apply some intelligence here and make this a more interesting problem. For example, when you have a partial board produced, I know I'm going to put 9 digits down the board, but if the first row already doesn't equal 15, what's the purpose of going on any further? And that's the weakness of this particular brute force implementation. It only checks to see if it's valid when all 9 digits are placed, when in fact I could probably find out a lot earlier whether that's the case. So I'm not even going to attempt to run solve of a 4x4, because that might take several weeks on this computer, the way that this algorithm is currently implemented. But I can make a small change, and I'll sketch that out here. Coming up a method called solveIt. Everything looks the same on solveIt. If I get to the n squared, I check to see if it's valid. I go through all the possible digits. As long as it's not used, put it in, do the recursive call, everything else is the same, but there's one difference. I add a short circuit called valid up to. I take the time to intervene after a row is full and check to see if that row is valid, because if it is valid, then maybe I should continue, but if it's not valid, I have to prune that whole search, and I could be throwing away trillions of possible dead ends that I know can't possibly work because I've checked this intermediate result. Recall how I said that a brute force algorithm has no intelligence in it, and it's true. But when it doesn't perform the way you want, well, then you have to apply some intelligence to see if you can prune away some of the ineffective branches that it's going to explore. What does valid up to actually do? Well, it says, what step am I on? And is that step actually the end of a row? If I get to the end of a row, I want to validate, is the sum of that row equal to what it needs to be? So I can always check anytime I want, but I can now take the opportunity to prune away ineffective searches that will not lead me anywhere. This is the first step, check to see if I've got every row. And I also take the added step to say, well, maybe I'm completing a column. So as I'm working through this two-dimensional board, I fill in every row, and as I fill in the rows, then the leftmost column will be completed. So after every row is full, I can continue to now check the columns. And with all this in place, I'm now able to take a problem which would otherwise have literally taken weeks. You see the search space. And instead write a small little enhancement which says, take a board, that's now a 4x4 board, as you see. This time solve it, but I'm solving using a different function, not the solve, the brute force one that used no intelligence, but the solve it. That still has its work cut out for you, don't get me wrong. It's still going to take a couple seconds. But instead of doing that brute force and no intelligence, I now have a 4x4 square, which is rather surprising considering how many possible arrangements there are, and in a matter of seconds I came up with one. Now I can take these, and with small modifications, I can have it not just produce the first solution, but to compute every possible solution. And that's something that you can find in textbooks, and maybe I'll add it into the final code when the video is completed. But as you'll see, if you're looking for a solution to a problem, and you don't know in advance any intelligent way to solve it, you can usually find a way to develop a representation of the problem and identify the moves, as abstract as that concept may be, that advance you towards a solution. And setting up a very simple framework to just brute force try every possible move from the initial board state, you'd be surprised that a whole range of problems that are human tractable can be turned out in the matter of seconds to minutes using a simple implementation. It's up to you to come up with the problems, but once you do, I bet you might find brute force works very well in a lot of cases. This now completes the module on the brute force approach. It's a surprisingly versatile approach for solving problems when you don't know in advance any particular way to solve it, and that in itself is useful. If you can frame the problem in a representation that records the state of the problem and then a set of moves that advances the problem one step at a time, you can use this structure to solve countless problems. Of course, the problem size has to be manageable. We use it to solve a pegboard of 15 holes. I think that could work for maybe 28 or 35 because the number of moves is very small at any one point in time. However, for the magic square sample problem, it can't really work for much more than a 4x4 because the search space is too large. However, as an approach that lets you solve problems without requiring much intelligence, it's extremely useful. And all I'm doing is let the program run for hours or even days, and at the end of it I might come back with an answer, which is certainly something that's a lot better than banging my head against a wall to try to find out what the answer is to the problem. Naturally, your mileage will vary. This particular algorithm is very susceptible to the speed of your processor and the actual representation, the compactness of the memory for that, and the ability to rapidly check if a move is valid and if a solution has been achieved. You can use this approach for countless problems, and I encourage you to investigate them and go as far as your creativity will allow. This ends the brute force module.